Okay, so now that we have defined a sigma algebra, we will define a measure um, on our sigma algebra. Um, so if we recall, we said that if we have a set, so we said let X be a set, M a collection of subsets of X such that and M had to satisfy a few properties. The first property that it had to satisfy was that it contained countable unions. And the second property is that it had to contain complements. Then M is a sigma algebra on X. So now the goal would be to um, the goal that we want is to measure our in some sense classically to measure the quote unquote length of a set. We want to find a way to assign numbers or um, assign values to our elements of our sigma algebra, right? So we want a function, right? So we want something called a measure. And a measure is so we have a definition. Um, so we have let X be a set with sigma algebra M. A measure on M is a function mu that maps M into, so we're going to require that our measure take on positive values, or zero, or infinity. So we're just taking on non-negative values. There are other things called sign measures that can take on negative values as well, which we will get to later. But mu has to satisfy a few properties. So the first property that has to satisfy is that mu of the empty set is equal to 0. So if we recall from last time um, that the empty set was actually an element of our sigma algebra. The empty set and all of X are elements of our sigma algebra. That comes from taking we can take the empty intersection to be intersecting a set with itself no times. I believe that's a good way. That's a way to get the empty set. But anyway, so we have this, and we want a condition called countable, or we want a condition called countable additivity. So if we have a sequence, e sub I equals 1 to infinity, and so we have a sequence of subsets of X. So this is a sequence in M, right? So this is in our sigma algebra. Then we want, so we require, so we want mu of the union of our e sub i's to be equal to the sum of the measures of the individual e sub i's. So this is called countable additivity. So these two conditions, um, this is what makes mu a measure. Now, there's some terminology to be noted. So, so if we have a set X with a sigma algebra mu, and with a sigma algebra M, and a measure mu is called a measure space. And there are some other things to point out. Um, if the measure, so this is just kind of like if mu of x is less than infinity, right? So if the measure of our whole space is finite, then we say mu is finite. And another type of finiteness condition we have if we can write x as the countable union of elements in our sigma algebra. So if x is the countable union of elements in our sigma algebra, so e sub I is in M for all I equal to 1 to infinity. Um, if we have this condition and if mu of e sub I is finite for all I, then we say mu is sigma finite. So this essentially just means that we can kind of break our space up. We can break our set X up into a countable a countable union of parts that have finite measure. The space itself doesn't necessarily have finite measure. The space itself doesn't necessarily have finite measure, but each piece has finite measure, and this is actually useful for a number of theorems later on when we get to um, like integration and stuff like that. If we require our measure to be sigma finite, um, and the last piece here is called is semi-finite. So if for each each element of our sigma algebra M, um, where mu of E is equal to infinity. So each element of our sigma algebra that has infinite measure, that if there exists an F in M uh, with F subset of E and 0 is less than mu of F is less than infinity, then we say that mu is semi-finite. So um, there this is kind of like I hesitate to call it an intermediate value theorem because it doesn't say that um, mu will take on every value between infinity and 0. It just says that um, for each it says that for each set of infinite measure we have a subset of it that has finite measure. So it's kind of like each set with infinite measure. If mu is semi-finite, then each set of infinite measure has a subset that is of finite measure. So this is kind of just another way to break apart our sets. Um, Now, the kind of cornerstone properties that we have, um, there are four very important properties that our measures will satisfy. So this is a theorem. So if mu is a measure on uh, on our set with our sigma algebra, then mu satisfies the following properties. So the first one is called monotonicity. So monotonicity says that if E and F are elements of our sigma algebra, and E is a subset of F, then mu of E is less than or equal to mu of F. The second condition is called subadditivity. So if we have any general sequence, in M, then we have mu of the union of E sub I is less than or equal to the sum of mu of E sub I. With equality coming, if the E sub i's are disjoint, then this is just our second property of being a measure. If the union is a disjoint union, then, but in general, for general sequences, they don't have to be disjoint. We have this subadditivity condition. Now we have two of the continuity conditions. So this is the first one is continuity from below. Continuity from below states that if we have a sequence in M, a nested sequence, so we have this nested sequence in M, then mu of the union of E sub I is equal to the limit as I goes to infinity of mu of E sub I. And this limit could be infinite, of course. So we have a similar condition called continuity from above. So we have the same setup. We have E sub I is a sequence in M, but this time we have E1 is a superset of E2, is a superset of E3, right? Where we have one additional condition, we require mu of E1 to be finite, then mu of the intersection of E sub I is equal to the limit of mu of E sub I. So these are our four conditions that we have. So we have monotonicity, we have subadditivity, continuity from below, and continuity from above. Okay, and we'll go through and we'll work through some proofs of these. So for the first item, let's prove the first one. So monotonicity. So if we have E subset of F in M, all right, so we have E and F in M, and E is a subset of F. We note that we can write, right? So our picture here kind of looks something like this. This is E on the inside, and this is F on the outside. We can write F as a disjoint union, right? So we can write F as E union F minus E, right? So F set minus E, that's going to be the set of all elements in F that are not in E, and E is just the set of all elements that are in A, of course, and taking the union is, of course, equal to F. Now this is good, right? Because since we have this disjoint union, we have that mu of F is equal to mu of E union F minus E, which is equal to mu of E plus mu of F set minus E. Okay, now from here we can notice that these are both positive. These are both positive measures. I mean, since our measure is positive, we know that mu of F minus E set minus E is positive. So this has to be greater than or equal to mu of E, which proves the claim. Okay, so that was a simple one. Now for 2, we want to prove subadditivity. Right, so we're going to have a sequence going to have a sequence in M. Now, this is just any old sequence. What we will define is we will define a new sequence. We'll have F1 is equal to E1. F2 is going to be equal to E2 minus E1. F3 is going to be equal to E3 minus E1 union E2. And in general, we have F sub n is going to be equal to, or I use K here, so we'll use K. F sub K is going to be equal to E sub K minus the union from I equals 1 to K minus 1 of E sub I. Right, so now we have this new sequence. So we started with a sequence in M, and we created this new sequence where we had F1 is equal to E1, F2 is E2 minus E1, F3 was E3 minus E1 union E2, and in general, we had this expression here. So Fk is equal to Ek minus the union from I equals 1 to K minus 1 of E sub I. Okay, so we had this general expression, and some things to note are that we have F sub j intersect F sub L is equal to the empty set. So these are actually pairwise disjoint if j is not equal to L. Okay, so how can we see this? So without loss of generality, let's just suppose that j was greater than L. Okay, now let's look at what we have. We have F sub j is equal to, by definition, Ej minus the union from I equals 1 to j minus 1 of E sub I, and F sub L is equal to E sub L minus the union from I equals 1 to L minus 1 of E sub I. Right, so what are these equal to? So if we expand this here, this is actually going to be E sub j intersect the union of E sub I complement, which is going to be equal to, which is going to give us F sub j is equal to E sub j intersect I guess we can just take it step by step and we'll keep it here. What does this one give us? This one gives us F sub L is equal to E sub L intersect the union of E sub I complement. Okay, so we have this. We want to show that they're disjoint, right? So if X is in F sub J, then in particular, we have X is in E sub J, right? Because if X is in F sub J, it's in E sub J, and it's in this the complement of this union. Right, so it's in the complement of this union. And we also have that X is in union of E sub I complement. But since J was since L, what do we have here? Since L was less than J, we know that L appears here. We know that E sub L appears on this side. So that implies that X is not in E sub L, which implies that X is not in F sub L, right? Because if X was in F sub L, it would have to be in E sub L. But we know that since this is because because L is less than J. That was our stipulation at the beginning, so we know that X is not in. That's what I meant, not in here, right? Because E sub L appears here, but we're taking the complement, right? So X is not in any of these guys, the complement of these guys. And just for reference, we know the complement here is going to be the intersection of the E sub I complements. So that implies, of course, that X is not in E sub L. So these are disjoint, which is good. And the next thing that we claim is that the union of F sub I, right, so the union of these F sub I's is equal to the union of these E sub I's, right? So with our initial sequence, right, so we have our initial sequence, and we form the sequence F sub k is equal to E sub k set minus the union from I equals 1 to k minus 1 of E sub I. And we claim that these unions are actually the same. So we'll show that they are. So if X is in the union of F sub I, then there exists a K in N such that X is in F sub K, but this implies that X is in E sub K intersect the union from J equals 1 to K minus 1 of E sub J complement. But this implies that X is in E sub K, which of course implies that X is in the union of the E sub I's. It's good. So we have the first conclusion. So we know that the union of F sub I is a subset of the union of E sub I. Now, if we suppose that X was in the union of the E sub I's, then of course X is in E sub K for some K, which implies that X is in F sub K, which is E sub K set minus, or intersect, a piece that I skipped. So in this line here, for some K, right, this is actually, what we want is, we can choose K to be minimal, right? So since we're working with natural numbers, we have a well ordering, right? So we can choose K such that X is in E sub K, but X is not in E sub J for all J less than K, right? So this is important because then we can say then X is in F sub K, right? Which is equal to EK intersect um, or set minus the union from j equals 1 to k minus 1 of e sub j, right? We know that x is in e sub k, but we also know that it's not in any element before. It's not in any set before e sub k. So x is not in the union of the e sub j's, and of course that implies that x is in f sub k. So that's good. So we have that we have a disjoint sequence. So we know that this is a disjoint sequence. So what we can do is when we take mu, so we have mu of the union of e sub j, right? We know mu of the union of e sub j, well, that's going to be equal to mu of the union of f sub j, or we could use I here, e sub I of f sub I, right? But we know that these are disjoint, so this is just the sum of the measures of each individual f sub I, right? But what we know is that um, we know that f sub I, right, is a subset of e sub I for all I. Now um, by monotonicity, we have that mu of f sub I is less than or equal to mu of e sub I, which that implies that the sum of mu of f sub I is less than or equal to the sum of mu of e sub I, which gives us that mu of the union of e sub I is less than or equal to the sum of mu of e sub I as desired. Okay, so that's good. So we've proved the we've proved countable, we've proved subadditivity. Now we want to prove continuity from below. So if we have a sequence of sets, a nested sequence, so we have a nested sequence of sets, what we want to show, so we want to show that mu of the union of e sub I is equal to the limit of mu of e sub I as I goes to infinity. Right, and we're going to use a little trick here, as we did in the previous example. We can create a new sequence, right? So if we suppose that E0 is equal to the empty set, create new sequence. So we create a new sequence f sub I, which is going to be equal to e sub I minus e sub I minus 1. Right, so this is a new sequence. So essentially what we're doing is, if we start, we could draw this out, right? This is E1, this is E2, this is E3. What we're doing is, so F1 is going to be the empty set. So F1 is equal to the empty set. F2 is going to be E2 minus E1, right? No, F1 is going to be E1. F2 is going to be E2 minus E1, which is going to be this region in here. Then F3 is going to be E3 minus E2, which is going to be equal to E3 minus, this is going to be everything at E1 union everything in E2, which is, of course, is just E2. So it's going to be this guy right here. And what we can also see is that just by looking at it here, we see that the union of the E sub i's is equal to the union of the F sub i's. Essentially, the union of the E sub i's is kind of overcounting because we have overlap, and the union of the S sub i's is taking well, the same material but removing all of the overlap. And this is clearly disjoint. It's disjoint by our drawing here, right? We could see that all of these F1, so this is F1, this stuff out here, this is F2, this stuff out here is F3. These are all disjoint. So what we have is we have mu of the union of E sub I is equal to mu of the union of F sub I, which is equal to the sum of mu of F sub I, right? Which is just writing F sub I out. This is mu of E sub I set minus E sub I minus 1. Now this sum is taken from I equals 1 to infinity, but we could pull that sum out and take the limit as n goes to infinity of the sum from I equals 1 to n mu of E sub I set minus E sub I minus 1. So what exactly do we have here? Well, we have that um, mu of E sub I set minus E sub I minus 1, that's going to be mu of E sub I minus mu of E sub I minus 1, right? Um, that's because um, E sub I is a subset of E sub I minus 1 is a subset of E sub I, right? This holds in general because if we have S subset of T, then we can write T to be equal to T minus S union T intersect S, which is going to be equal to T minus S union S. So mu of T is going to be equal to mu of T minus S union S, which is going to be mu of T minus S plus mu of S, since these are disjoint. So we get mu of T minus S is equal to mu of T minus mu of S. So this is just kind of like a general rule of thumb here. So we see we get this. So we get this up here. So if we look at the sum from I equals 1 to n, mu of E sub I set minus E sub I minus 1, that's going to be the sum from I equals 1 to n, mu of E sub I minus mu of E sub I minus 1. Right, and when I is 1, we're just going to get this term here is going to be 0. So we just get mu of E1 plus the sum from I equals 2 to n mu of E sub I minus mu of E sub I minus 1, right? But writing this out, we just get mu of e sub 1 plus mu of e sub 2 minus mu of e sub 1 plus mu of e sub 3 minus mu of e sub 2 plus all the way through plus a mu of e sub n minus mu of e sub n minus 1. All of these terms will cancel out except mu of e sub n. So we get that the sum of mu of e sub I minus e sub I minus 1 is equal to, actually it's just equal to mu of e sub n. So in the limit, right, so we took the limit as n goes to infinity of the sum of mu of e sub I minus e sub I minus 1. That's just going to be the limit as n goes to infinity of mu of e sub n, which is exactly what we wanted. Now, the last piece of the puzzle is continuity from, which ones have we done so far? We want continuity from above. Right, so if we have a sequence, E1, E2, where mu of E1 is finite, what we can do is, so we want to show that mu of the intersection of e sub I is equal to the limit as I goes to infinity, mu of e sub I. Right, now to show this, what we can do is we can notice that that the intersection of e sub I from I equals 1 to infinity, that's actually going to be equal to e sub 1 set minus e sub 1 set minus the intersection of I equals 1 to infinity of e sub I. Right, how can we see that? Well, if x is in the intersection of e sub I equals 1 to infinity, right, so if we expand this out, let's expand this. So this is going to be E1 intersect E1 intersect the intersection of EI complement, right? This is going to be E1 intersect, and in the complement here, this is going to be E1 complement, right? Union, and then this intersect, this complement cancels out, so we just get E sub I. Right, so of course if x is in the intersection, this implies that x is in E1, right, which implies that x of course is in E1, which implies that x is in E1 intersect E1 complement union the intersection of E sub I. Right, of course, since if x is in E1, then x can't be in E1 complement, but that's okay because that means that x is in the intersection of E sub I, which is of course true. So if so that's the forward direction, and the reverse direction is if x is in E1 intersect E1 complement union intersection of E sub I. This implies that x is in E1 and x is in E1 complement union the intersection of E sub I. And this, of course, is from I equals 1 to infinity. But since x is in E1, x can't be in E1 complement, so that implies that x is in the intersection of E sub I. So we have this equality. Now, we can, what we can do from here is simply look at, right, so we have mu of the intersection of E sub I, that's going to be mu of E1 set minus E1 set minus the intersection of E sub I. We know that this is a subset of this, so this becomes mu of E1 minus mu of E1 set minus uh, the intersection of E sub I. Well, what does this become then? Well, this becomes mu of E1 minus, in here, this becomes mu of E1 intersect the union of E sub I complement, like what we had up here. But this is just going to be mu of E1 minus mu of E of, right, we could pull E1 on the inside. So this is going to be the union of E1 intersect E sub I complement. Well, that's just going to be equal to mu of E1 minus mu of the union of E1 set minus E sub I complement, right? So let's write it on another page. So we have, this is equal to mu of E1 minus mu of, right, mu of the union of E1 minus EI. So what can we say about this? Well, this is actually this is a disjoint sequence, right? What do we have here? Well, E1, so we have, this is E1, this is E2, this is E3, right? E1 minus E1 is of course the empty set. E1 minus E2 is going to be this. E1 minus E3, right? So E2 is this in here. E1 minus E3 is this. So this is actually not a disjoint sequence, it's an increasing sequence, right? E1 minus E1 is a subset of E1 minus E2, which is a subset of E1 minus E3, right? So we have an increasing sequence, so we could use continuity. We can use continuity from below, right, to write this to be equal to mu of E1 minus the limit as I goes to infinity, mu of E1 set minus EI. But of course, EI is a subset of E1 for every I. This is mu of E1 minus the limit as I goes to infinity, mu of E1 minus mu of EI. We could pull mu of E1 outside of the limit. So we have mu of E1 minus mu of E1 plus the limit as I goes to infinity of mu of EI. But this is good because we know that mu of E1 is finite, so we can cancel these, and we're just left with the limit as I goes to infinity, mu of EI. So in conclusion, we have proven all of these nice properties that our measure should satisfy, right? So if we have a measure, we have this monotonicity property, where if the measure respects subsets, we have the subadditivity. That's just a general statement about sequences of sets. They don't have to be disjoint. So any sequence of sets, the measure of the union is less than or equal to the sum of the individual measures of each piece of the union. And we have continuity from above and continuity from below. Continuity from below states that if we have a nested sequence, a nested increasing sequence, then mu of the union of the E sub i's is the limit of the measures of each of the individuals E sub i's, and continuity from above says the opposite. If we have a decreasing sequence where the measure of the first sum is finite, then the measure of the intersections is going to be the limit.